Share my screen. So as usual, start with the 9x9 nonlinear flight dynamics, right? And we know that symmetry and linearization about symmetric flight condition led to decoupling of this 9x9 into 4x4 longitudinal flight dynamics. So this is any symmetric motion along the XZ plane of symmetry. And please stop me, whether you studied or not, please stop me anytime. So this is motion in that plane. Oopsies. Variables, anyone remembers variables? U, right, W, Q, and this angle is theta. So these are the four variables, and last time we considered these four variables. Last lecture was mainly about the longitudinal flight dynamics. This lecture is on the other branch, the 5x5 lateral flight dynamics. Lateral, so anything out of the XZ plane, anything that takes you out of the plane of symmetry, any motion that is not symmetric, any motion where the right wing is not seeing the exact same thing like the left wing. So side slip, roll, yaw, anything that we did not account here. So let's take this from the lecture notes, the state space model. Oops, where is it? Lecture 15. So this is basic tools, snapshot. Okay. So here is my state space model governing the lateral flight dynamics. So V, again, we're trying to remember together that table that has all the variables should be always in the back of your mind. So V is the side slip, and indeed, I'm reminding you that in the same fashion like W is an angle of attack, V is also side slip angle. Indeed, the side slip is approximately V over U naught. Okay, so whenever I mention little v, I really mean the side slip angle. P is the roll rate, R is the yaw rate, phi is the roll angle, psi is the yaw angle, and linearization made things simple here with respect to the Euler angles, because now look at this equation, phi dot equals 0 everything and 1 times P. So this equation is simply phi dot equals P, right? The rate of change of the roll angle is the roll rate. The same here, the rate of change of the yaw angle is the yaw rate. Super simple, okay? In order to play with this system, I need to get the A and B matrices as numbers, and let's look at what we have in the A and B matrices. The A matrix is full of these stability derivatives, and we have seen these before. We derived expression for LP in the lecture, and you guys did in the homework for NP, also in the lecture for NR. But what are these dashes? So we have seen LP, but not LP dash. So let's just take a minute here to define these dashes. Actually, any L dash is simply L plus IXZ over IX multiplied by N, 1 minus IXZ squared divided by IXIZ. And the same for N dash is also N plus IXZ divided by IZ, L, 1 minus the same thing. So what is this? It's actually due to inertial cross-coupling. Let's see. If IXZ the product of inertia, Ixz, is 0. Let's put Ixz is 0. If you put it 0, this goes away, and you have n dash equals n, and also L dash equals L. Okay, so if Ixz is 0, to us, you can drop the dashes, that's fine. So these will be the rolling and yaw moment that we are familiar with. If it's not 0, then what are these dashes? Well, we know from the beginning that roll and yaw are coupled aerodynamically, but this is more. So when we apply, say, rudder deflection, we get yaw moment, right? But also we get roll moment. Okay, so but this is from aerodynamics. Roll and yaw are coupled aerodynamically. Here we're not talking about this. Here we're talking about something else. Even if I apply pure roll moments, if I played with the rudder and the aileron together to apply pure roll moment or pure yaw moment, let's stick to one of them. Say pure roll moment. So I apply to the airplane a pure roll moment. I just hold the airplane and roll it with my hand. What will happen, even though the airplane will experience roll and yaw together? So this L dash is the effective rolling moment. N dash is the effective yawing moment. Each one of them includes both L and N through the coupling term Ixz, okay? The product of inertia. Any question about that? So inertially, what I'm trying to say is that inertially, when I apply pure roll or pure yaw, I will get both, okay? Because they are inertially coupled. This is in addition to the aerodynamic coupling. All right, we know what are these dashes now. Let's please get them for a specific airplane to study it and see, because I want to study this system. I have a dynamical system. I want to study its stability. How can I study its stability? Any clue? Any idea, any suggestion? How can I study stability of this system?
Get the eigenvalues and make sure that the poles are on the left-hand side.
Very good. Let's get the eigenvalues. So I need these numbers. Like I said, we have expressions for them without the dash. Okay, substituting these equations to get the things with the dash. For this particular example, we're given the numbers for this general aviation airplane that we played with last time. So these are the numbers. If this is too large, maybe I can just get this. These are the numbers for the general aviation airplane that we played with last time for the longitudinal modes. Again, it's general aviation airplane, which is a small, light airplane you fly for training and for recreational purposes with your friends. You can pay like $100 in John Wayne Airport and take one airplane for a trial. Not, I mean, someone will take you. And so this is the U naught is 176 feet per second. Span, if needed, because now we're talking about lateral, and remember guys, for lateral, the characteristic length or the reference length is not the chord anymore, but the span, if you remember. And luckily for this particular example, Ixz is almost 0. Okay, so we're gonna take it 0. So we don't need to worry about the dashes, and I don't want you to worry about the dashes in this course. If you ever need it in your life, then okay, here is the definition. But just for the sake of to focus on the physics, flight physics, let's ignore the Ixz for the moment. So when I talk about L dash, it is really simply L, which is the rolling moment, the aerodynamic rolling moment, and the same for N. Okay. So let's substitute by these things here in the matrix. I get the matrix full of numbers. It's 5 by 5 type Eig of the matrix A in MATLAB. You get the eigenvalues, right? So it's 5 eigenvalues. And stop me anytime, please. This is real, this is imaginary axis. 5 eigenvalues, one of them will be exactly at the origin. And this can be easily seen. Look at this. We have a column that is full of zeros, right? So for any matrix that has a column that is full of zeros, or a row that's full of zeros, I mean, you will get a zero eigenvalue. So I have one eigenvalue at the origin, exactly at the origin. What does it mean? So if I have an eigenvalue in the right half plane, this is an unstable system, right? But what does it mean if I have one right at the origin? Well, if this is one of your variables, real variables, then it means that your system is critically stable. But here, why this is expected? Because look at this. This fifth column is all zeros, which means that what? So this is the side force equation, the y equation. It's 0 times psi, so it doesn't depend on psi. The same here doesn't depend on psi. All of our equations do not depend on psi. Psi is the heading angle of the airplane. So your dynamics does not depend on the heading angle. And this is, of course, intuitively expected. If the airplane is heading to the east, it has the exact same dynamics as if it's heading to the north, if it's heading to the south. The heading angle does not affect your dynamics, right? So this is expected from the beginning, and we hinted to this sometime before. We said we can really reduce this 5 by 5 to 4 by 4 whenever we need it, okay? So whenever we have this kind of scenario, actually we call this ignorable variable or ignorable coordinate. When you go to the graduate school 241 dynamics, we really call it ignorable coordinate. Your dynamics does not depend on this coordinate at all. So it's an ignorable coordinate. You can ignore it. It doesn't affect your dynamics, but if you continue with it, you will always get an eigenvalue at the origin. Let's see. What does beta approximately equal? Beta is a variable. It means it changes during the flight, right? If your experience is a disturbance, it will keep changing. The nominal value for it during cruise is, of course, 0, right? It's the side slip angle. Or I don't know if you're asking about its name. It's the side slip angle. This is side slip, right? We have considered it before in the first half of the course. Yes, it's V over U naught. Oh, I'm sorry. You're asking about this equation. It's V over U naught. Very good. Thank you, guys. All right. So any question about this thing, about the ignorable coordinate? So this will correspond to an eigenvalue at the origin. I'm going to ignore it now. I'm not going to put it.
I had a quick question, Professor.
Yep.
Maybe it's jumping a little bit ahead, but I know you say that the ignorable coordinates, the pole at the imaginary axis will cause nothing to happen, right? Like if it gets a perturbation, it'll stay exactly where it is.
Very, very good. Yes, exactly. So yeah, go ahead.
So my question is, what's the difference between that and marginally stable? Because I know marginally stable, I think
this is marginally stable. So this is a good point. So you said exactly like Jeremy was saying. If you have an unstable system, if it's touched, if you have an eigenvalue in the right half plane, in the right, so the system is unstable. If it's touched by any disturbance, it will blow up. If all your eigenvalues are in the left half plane and the system is stable, then if you're touched, then the system will go back to its equilibrium. But if you have an eigenvalue exactly at the origin, one eigenvalue at the origin, and if the system is touched, what will happen? It will neither blow up nor come back to its equilibrium. So it will stay there, right? So, and this is exactly what happens for the heading angle. So the heading angle of the airplane, if it's disturbed, if the heading is disturbed, it will not come back and it will not blow up. Why? Because simply, look at this, all the equations don't depend on the heading. It's as if the airplane did not feel the disturbance at all. This disturbance did not affect the dynamics, so it will simply remain there, okay? So yes, from this perspective, the heading angle is critically stable. But this is expected because it's an ignorable coordinate. Any ignorable coordinate will behave like this. This is what I'm trying to say, is that this is not an issue. This is not a stability issue. We will not accept it if it's side slip, for example, or an angle, if it happens with the side slip or angle of attack or any of the important or real variables that are not ignorable. We will not accept this kind of behavior, so that when the angle of attack is disturbed, we don't come back, we just stay there. This will not be accepted. But for the heading angle, it is acceptable. The pilot will have to interfere to correct the heading of the airplane, or your autopilot. Okay.
Thank you.
All right, so now let's focus on the remaining 4x4. This is my 4x4. Give this to the MATLAB and type Ig, or just, it's fine, type for the full matrix and ignore the 0 eigenvalue. 4 eigenvalues now. And again, this is representative for almost all airplanes. Any conventional configuration will behave like what I'm describing now. So an eigenvalue on the real axis that is very close to the imaginary axis sometimes even becomes unstable and go to the right. So this is one. Another couple here, and again, this is not to scale. Oopsies. Let me put it here. 2, 4, 6. 2, 4, 6. So the blue one, the blue eigenvalue was at how much? This is negative 0.0098, very close to the imaginary axis, but it's stable in this particular airplane. For some other airplanes, it may cross the imaginary axis. It's still real, but it's still very close to the imaginary axis. The red ones, the real part is negative 0.49. And the imaginary part is 2.31i. So this is negative. All right. So as you guys know, we can get, oh, what happened? No, please. Yeah, very good. Okay. We can get the omega n, right? The natural frequency. This is just the diagonal. For this mode, it's about 2.37 radians per second. So it gives you how fast this mode is. And the real part is simply zeta omega n. So if we get the omega n, we can get zeta for this mode. It's around 0.21. So these are 3 eigenvalues. The 4th eigenvalue is here, very far. Again, this is not to scale, and this is negative 8.43. So it's very far from the imaginary axis, relatively. So how many modes, when you look at this picture, how many modes?
3.
3. So there is one mode here, the blue mode. Then the second mode is the red, and it's complex conjugate, so it's oscillatory mode. You know, if it's complex conjugate, then it's oscillatory. And then the third mode is not oscillatory, the green mode, and it's too fast, right? This is very fast. Remember, what is the settling time? It's 4 divided by the real part. The real part here is 8, so it's like half a second, less than half a second settling time. Okay. So this is very fast. Actually, this is the fastest mode in airplane flight mechanics, even faster than the short period mode in the longitudinal flight dynamics that we discussed last time. Remember, last time we had only 2 modes in longitudinal flight dynamics. One was complex conjugate, very far from the imaginary axis, and one was complex conjugate, but close to the imaginary axis, right? So this is even faster than the short period. This is the fastest mode of the airplane. Fine, so we have 3 modes, but still, all what we can conclude from this picture is that it seems that the airplane is stable, right? All the eigenvalues are on the left half plane. And we need to learn more about its dynamics. So how can I know? Let's pick them one by one. Let's pick the green mode. How can I know the variables that are most associated with this mode? Any idea?
You need to obtain the associated eigenvectors with each eigenvalue.
Exactly. So remember, when we do Eig in MATLAB, we can do V and D. Then this V is a matrix that has all the eigenvectors, right? So you're going to pick the eigenvector that is associated with this green mode and look at it. And like I said last time, it's a vector, so it will include what? It will include the changes in the states, delta V, delta P, delta R, and delta phi. And please let me stop here if you don't know what any of these variables mean, if you don't know. So V is the side slip velocity of the airplane. The airplane is moving forward, but sometimes it's slipping to the side. So this is the velocity of slip. P is the roll rate, roll angular velocity. R is the yaw angular velocity. Phi is the roll angle. Phi dot is P. Okay. So we're gonna read this vector from the MATLAB, but like we did last time, I cannot compare really, because what really matters is not these numbers, but the relative magnitude. How do they compare with respect to each other? And I cannot compare meters per second with radians per second with radians. So let's do what do you suggest in this case?
Non-dimensionalize again.
Very good. Non-dimensionalization. Non-dimensionalizing. All right. And when we non-dimensionalize, so we're gonna divide delta V by some reference speed. Of course, it's U naught, our reference speed. Delta P, we're gonna non-dimensionalize as usual. If we divide by U naught, I need to multiply by a length, and the lateral or the reference length and the lateral is B over 2, as you guys remember. Then this is R is the same. So this is B over 2 U naught. And delta phi is already non-dimensional. It's an angle. It has a unit, but it doesn't have dimension. Then the next step, like last time, we do normalization, right? So we do normalization. Let me do it here. What is normalization? This is not necessary step, but it's convenient. Just pick one of them and divide by. So we're going to divide everything by delta phi. So the last entry of this vector will be delta phi by itself, so it will be 1. And let me read this vector now from the notes. And again, the notes of this lecture and last lecture are quite detailed, not like any other lecture before where we just provided the summary, because these two lectures include lots of physics of flight. So here is the vector after non-dimensionalization and normalization. And we're going to look at this vector to see what are the variables that change the most. What do you think? What are the variables that change the most? Come on, folks.
The one that's boxed.
The yawing.
This is
angular momentum or
the what?
angular velocity.
The angular velocity, roll angle. P is one of them. So the roll rate, and phi, the roll angle. So it's mainly the rolling motion of the airplane that is really triggered in this mode. The rolling motion of the airplane that is excited in this mode. It's actually, the name of this mode is quite expressive. This is what we call the rolling mode. It's pure rolling. So this is the rolling, this is the mode number 1, this is the rolling mode. Sometimes they call it the rolling mode or roll mode, okay? Fine, so this mode is quite fast, it's too fast. So usually if we have almost pure roll, it will behave according to this mode, which means it will behave fast. It will follow the pilot command fast, it will reject disturbance fast. And this is really, you feel it in flight, whether you're passenger or you're flying the airplane. If you're a passenger and And if you feel that the airplane is disturbed in roll, it comes back immediately. Like we said, the settling time here is around half a second, and this is what you really feel. If the airplane is disturbed in roll, it just come back very quickly. Whereas if it's disturbed on a vertical pump or something, I mean, you will feel the oscillations. It takes a while. You feel it yourself. So the rolling moment, the rolling mode is the fast, or the roll response of the airplane is quite fast. It's not oscillatory, right? And all of this we get from just by this analysis. We get the eigenvalue, get the corresponding eigenvector. We know we get a lot by this simple analysis. Any question about that?
Yeah, Professor, what are we looking for when you ask which variables affected the most? Like what should we be looking for?
We look here and see what are the largest magnitudes. So the largest magnitude, this is 1, this is 0.8, anything else is 0.0 something. So the roll rate and roll angle is really the largest here. So this mode is mostly associated with rolling motion of the airplane, which means, okay, so why we're doing this? Because when I don't like the rolling motion, the rolling behavior of the airplane, I don't need to go and mess up with the entire 9x9 nonlinear flight dynamics, or even the 5x5 linearized lateral flight dynamics. You will just get swamped in these numbers and this 5x5 matrix. Here, we just learned that if you don't like the rolling behavior of the airplane, it is just this mode. Go and play with this eigenvalue in particular. How can I do that? Okay, how can we do that? Let's get an approximation. Again, like I said before, whenever we have 4 eigenvalues, in general, we don't usually go and say this eigenvalue is associated with this variable, this eigenvalue is associated with that variable. Usually we don't say that. But in some systems, there are some decoupling of the physics. How we get to know about this decoupling? By this eigenvector, by scrutinizing the eigenvector. And this is what we're doing. When we look at the eigenvector, we learned that this eigenvalue is really mostly associated with rolling motion. The other motion can be neglected. It's small contribution. Okay, now how can I get an equation of motion for this rolling mode only? An approximation. How can I approximate this one? Because this came from where? It came from the 5x5. I don't need to play with the 5x5 every time. I need to get an analytical expression, approximate analytical expression. Can I do that? Well, let's see. The eigenvector says that it's mostly rolling motion. Neglect anything else. So let's get the rolling moment equation. This one. And neglect anything else. Ooh. So the P dot equals LV times V. Well, we just said we're going to neglect everything else. So we're going to neglect V. Okay. Plus LP times P. So we have this term. So here is P dot is LP times P plus. We're going to go and keep reading. LR times R. Well, again, we're neglecting the R, the yaw rate, because it's too small contribution. All right, and we go here, L delta aileron times delta aileron. Indeed, the aileron is my main controllers for the rolling motion. So, and we're done. So this is your rolling, what we call the rolling approximation. Is it a successful approximation or not? Well, let's get the eigenvalue out of it and compare it to the actual eigenvalue. So remember, it's just one state, it's one equation, it's one state. So this is my x, the P here is my state x. So this is x dot is A. This is A matrix for the rolling, but it's not a matrix, just a single number, it's a scalar, right? It's 1x1 matrix. And this is my B, right? B for the rolling. This is my input, this is my state. Any question about that?
Did we exclude the second input, delta rudder?
You don't need to, but when we there is no need to have two inputs for one state. Of course, this is over actuation. And if I'm gonna pick one, which one should I pick? The aileron or rudder for controlling the roll motion? It's indeed the aileron, right? This is why we have the aileron for the airplane a priori from the beginning, is just to control the roll motion, right? It's a good question. So this is my state equation, x dot equals ax plus b times the input. And my A matrix is just a scalar. So if your A matrix is a scalar, how much is the eigenvalue of A? What is lambda rolling? Well, if my matrix is just a scalar, the eigenvalue is the same as the scalar. So this is just LP dash. And LP dash was negative 8.4. So this approximation gives the eigenvalue of the rolling mode as 8.4 versus it was negative 8.43. So it's less than 1% error. It's very accurate approximation for the rolling motion of the airplane, which was expected to be accurate. Why? Because the eigenvector was clear, was crystal clear. It's just rolling motion. And if I want to get a transfer function, let's get a transfer function from here. Remember how to get a transfer function? The easy thing, replace each dot with
S.
Yep, so this is the Laplace transform. So this is SP of S equals LP dash P of S plus L delta aileron, it's a constant, times delta aileron of S. And now we need to ask ourselves, what is the input and what's the output? Because the transfer function is the output in the S domain divided by input in the S domain. So what is the output? What is the input first? What's the input in this motion?
The aileron.
Aileron. And what's the output? The output would be the roll rate. So this is P divided by delta aileron. So this is equal. So I need to get the P's together, aileron, and then divide P divided by delta aileron. So this will be L delta aileron S minus LP dash. So this is your transfer function if you ever need it, right? And it's first order system. It's not second order system. So it's not oscillatory, which means that if the airplane is perturbed, this is some P naught. This is P as a function of time. If the airplane is perturbed to some initial roll rate, it will just go like this, right? There is no oscillation. It will not go like that, right? It will not go like that because it's not a second order system. It's a first order system, and not only a first order system, but also a fast one, right? Its settling time is like half a second. Where is the eigenvalue or the pole? Well, here's the pole. It's at LP dash, which I know from the state space model, right? Any question about that? Any question, please? Any question about the rolling motion? Any question about the rolling motion, the rolling mode of the airplane, the green mode? So in the lateral, we identify three modes. The first, which is the fastest mode of the airplane, of all the modes of the airplane, whether longitudinal or lateral, turns out to be the rolling mode. Okay. Any question?
Professor,
Why? Yeah, go ahead.
I came in late. Could you go back to the top?
Mm-hmm.
And for L prime, when you say equals L plus, you know the equation of L prime and N prime. Can you explain that again, please?
Yeah, we were just saying that this is the effective, so P dot is the roll, so P is the roll rate, so the dot is the roll acceleration. So the roll acceleration is simply equal to what? To the rolling moment, right? Divided by moment of inertia. So P dot is the rolling, what should come here is the rolling moment divided by moment of inertia. So anything here is the effective rolling moment. So L dash is the effective rolling moment, N dash is the effective yaw moment. Sometimes the roll moment, the effective roll moment comes from an aerodynamic roll moment, L, but because of the coupling, when you apply N yaw moment, aerodynamic yaw moment, it actually causes also roll. And the same here. If you apply roll moment L, aerodynamic roll moment L, it causes an effective yaw moment N dash. So the dashes are the effective ones. The ones without the dashes, these are the aerodynamic ones. And because of the coupling, when you apply only one of them, you get two. You get the two. The coupling is through IXZ. So if IXZ is 0, L dash is L and N dash is N, which is the case here. But
Professor,
Yes.
in reality, is that coupling working in the same direction as the aerodynamic coupling or in the opposite direction as the aerodynamic?
Not necessarily.
Okay.
We're gonna talk a lot about the aerodynamic coupling today. Most of the lecture will be spent about the aerodynamic coupling. Okay. Because there are several sources for aerodynamic, but the inertial one is favorable in the sense if you apply yaw to the right, you will get roll to the right also from this inertial coupling. Okay. But whether it's the dominant or not, it really depends on the airplane. Like you see the IXZ. Yeah. Okay. So let's see. Okay, so we're done with the rolling moment. The rolling approximation. Any question about the rolling mode?
Professor?
Yes.
So we look at our eigenvalue, we're approximating it to be our LP, like LP.
Yes.
What right below you have another variable like V sub delta negative 8.43.
Versus, I'm sorry, this is versus. This was the exact value coming out of the 5x5 matrix. And this is the simple one coming from this very simple analytical expression, which says that lambda rolling is approximately given by LP dash. LP dash here is simply LP, right? Because there is no IXZ, and it's negative 8.4. So when you substitute this, you get negative 8.4, but the exact value of the eigenvalue was negative 8.43. This is versus. I'm sorry, it's not.
Can we always make that assumption, like with other?
Yes, these are standard modes. These are standard approximations. So when you find a book or a paper or a report, or you write a report, you're working on an airplane and a new configuration for an airplane, and you determine your roll mode. You say, here is the eigenvalue of the roll mode. So the community knows what you're talking about. These are standard approximations. This is versus. And why do we need to, why should we, because getting the eigenvalues of 5x5 matrix is not a big deal. I mean, we have MATLAB, we have everything now, not like 50 years ago. But the point is, this is a simple analytical expression, right? First of all, it's damn accurate. It's less than 1% error. Second, it's a very simple analytical expression. It tells you that the rolling mode is simply governed by your LP, the stability derivative LP, where we derived an expression for LP, right? So in terms of the airplane geometry. So if you don't like it, you can go and play with the airplane geometry to adjust the eigenvalue and the behavior of the roll mode of the airplane. Whereas from the 5x5, you can never see this, right? I can never see what variable here that affects the roll mode. Okay, so this is why this is why we indulging into the eigenvector analysis and doing rolling approximation, all approximations, to get simple analytical expressions so that we can understand what is the underlying physics. What are the variables mostly affecting the rolling behavior? Well, it's the LP of the airplane. And in lecture 11, we derived expression for the stability derivatives, in particular for LP, in terms of the airplane geometry. Questions?
I had a question about the blue part at the bottom. We add the variable s. What does it stand for, or is it just arbitrary?
S is the Laplace variable. So, like here we are, for this eigenvalue, S is negative 8.43, right? Here, S is negative 0.0898. So S is the Laplace. So this is, I guess you guys have taken Laplace before, right? Yeah, S is the Laplace variable. In order to get a transfer function, you must have, we need to turn the differential equation into the Laplace transform.
And it's just basically a study of the frequency domain, right? Instead of the time.
So that's a good question. S is not exactly the frequency, but it's very related to the frequency. Yeah, the domain is not exactly the frequency, but it's very related to the frequency. When you put S equals j omega, so when we focus on things on the imaginary axis, then we go into the frequency. So in this transfer function, if you put S equals j omega, then we are in the frequency domain. But in S is not the frequency domain. This is very related to it.
Oh, that's interesting. Okay, thank you.
All right, so let's see. So we're done with the green mode. Let's go to the red mode. It's actually called the Dutch roll mode. And for a reason, funny reason though. So let's see let's see the eigenvectors, right? To see what is the motion associated with this. It's relatively fast mode. It's not very well damped. It changes from one airplane to another, but this is typical, really. So let's see what is this mode. So it's an oscillatory mode. What variables oscillate? We're gonna do the same. We're gonna do here non-dimensionalization, normalization. So now we're gonna do this for these two eigenvectors corresponding to the red eigenvalues. So let's read that. And since they are complex conjugate, the eigenvectors also are complex conjugate. So these are the complex conjugate, the eigenvectors for the Dutch roll mode. And let's determine what variable, let's take them variable by variable. By the way, this is two eigenvalues. So we're talking about two variables, right? Mostly. So if we're going to do an approximation, we're going to do two by two system. So let's take them one by one. What is the variable that changes the most? What's the variable with the largest magnitude?
The top one, the delta delta 5.
The sound is not very clear, but if you look here, this is larger than 1, right? So it's indeed beta. So it's side slip. So this mode is mostly associated with side slip, oscillations in the side slip. So the airplane, you know, side slip to the right, then side slip to the left. That's interesting. What else? Well, if we compare the roll and yaw rates, because this is the roll angle, I cannot compare the roll angle with these guys. If I am to be fair, I need to add the yaw angle and compare. So let's compare the rates, because the angles will go the same. Let's compare the rates here. So I mean, they are both of the same, almost very similar magnitude, right? This is 0.22, this is 0.24. So they are very similar magnitude, but unfortunately, I'll have to ignore one. Seeing that this is slightly larger, the R. So indeed, this mode is associated with all of them: side slip, roll, and yaw. So oscillations in side slip, roll, and yaw. This looks like this. The airplane in this mode behaves like a tree leaf. So it keeps oscillating in, do you see, oops. Do you see this picture? Come on, what happens? All right. I don't know why it's happening. Okay, very good, very good. I think this is good enough. Okay, so this is, you see, the airplane oscillates in side slip and also roll and yaw, all of them. Okay, so it goes like a tree leaf. Any question about this? Do you understand this picture? Any question? It's an oscillatory mode because it's complex conjugate, and it involves the three of them, but we know that the largest change is for beta, the side slip. So there's really large oscillations in side slip.
So is this aircraft kind of like swooshing side to side, or is it losing altitude as it's also doing
That's
this?
a very good question. It goes side to side, but also loses altitude. Whenever you do roll, if you don't compensate, you will lose altitude, right? Because what is vertical now is only part of your lift, is not the total lift. So if you didn't increase your lift by increasing the angle of attack or anything else, or your speed, you will lose altitude, always. So, but we're not focused on the altitude here. Why? Because losing altitude is really in the other plane, right? We're just focusing here on the lateral motion, the out of plane motion. So let's look at this. The airplane, like I said, goes like a tree leaf. Okay, it's a nice oscillation. The issue is this mode is quite fast. So actually this mode is quite annoying to passengers, as you may expect, particularly if you're sitting back towards the vertical tail. I mean, close to the tails, because you're far from the CG, so you will feel the oscillations, the lateral oscillations. This mode is annoying to passengers. It's annoying to pilots because it's fast. If it goes unstable, they will really struggle and may not be able even to stabilize their plane. Unlike this mode, for example, remember, if you have a mode that is unstable but slow, very slow, that's fine. It will take quite a bit of time until it blows up, and the pilot will have plenty of time to intervene and prevent this instability. But if you have an unstable mode that is fast, then this is quite dangerous. Okay, the Dutch roll mode is fast, is relatively fast. Okay, and it's not well damped, so it's annoying to passengers, annoying to pilots. It involves oscillations mainly in side slip, but also in roll and yaw. Probably yaw is larger than the roll, as we see from these eigenvector analysis. Any question about that?
This one's pretty minor, but in the third row of our matrix there, it's minus plus instead of plus minus. Is there like, is that just error or?
No, it's not an error. Yeah, that's a good question, Derek. It's not an error. Because remember, these are two eigenvalues. That's a good question. It's the two eigenvalues. They correspond to two eigenvectors. So actually, this is here we're lumping two vectors together, but they are complex conjugate. Okay, what is the first vector? It's this number with the plus, this number with the plus, this number with the minus. The second vector is this number with the minus, this number with the minus, and this number with the plus. Do you see what I'm saying?
Right. Yeah.
Okay. Yeah. Which is interesting. Why? Because it gives you, I don't want to spend quite much time with this, but as we discussed last time, this will give you how the phase will behave. So this means what? This means that the roll, this is the roll, right? The second is the roll. So the roll rate is in phase with the side slip. I mean, if this is plus, this is plus. But here the yaw rate, the imaginary part, is actually out of phase with them. So anyway, it gives you a little bit of idea how the oscillations will go if you indulged in the analysis of the eigenvector itself. But it's not of our concern now. What to my concern now is I need to know more about this mode. Like what are the stability derivatives that are mostly determine the behavior of this mode, determine the speed, the omega n, and the damping zeta, so that if I need to adjust the airplane geometry, I know where to go. Just by knowing these two eigenvalues from the 5x5 matrix, if I don't like this mode, it's too low damping, for example, and the pilot and passengers don't like it, how can I change this mode? Just by the 5x5, I have no clue what of these stability derivatives really affect this mode. To get that, we need to get an approximation. Go from 5x5, focus on only 2x2 system that mostly represent these two eigenvalues. How can we do that? Through this eigenvector analysis to determine what are the two variables that are mostly associated with it. Well, we determine as for first approximation, I mean beta for sure, but and there is P and R, but it seems for first approximation, R is slightly larger than P. So we're going to consider B and R, beta and R. And again, these are standard modes. It's not like we're deciding them together based on these numbers. This is for any airplane. So we're going to do a Dutch roll approximation. Dutch roll approximation. I didn't tell you what is the reason for the name, because if you look at this, it really looks like skating, right? And guess who are mostly known for skating? They're the Dutch. So it's as funny as this. So this is the Dutch roll approximation. Let's go now. We decided that it's beta and R. Anyone that does not agree that it's beta and R, side slip and yaw, if I'm to pick two, because there are two eigenvalues, if I'm to pick two, they're going to be the side slip and yaw rate. Because the rest is easy. Why? It's beta or V, right? Because in my original writing, we have V. So we have V and R. So it's the first and third row, first and third column. This is my state space model, easy enough, right? So you're going to write here d by dt. My states are V and R equal some matrix, which I don't know, times the same states, V and R. This is my A Dutch roll, which I need to fill. And I'm going to fill it from the original equations of motion. That's easy, 1, 3, and 1, 3. So this is YV negative U naught NV dash NR dash. Any question about that? This is a 2 by 2 matrix. I can determine analytical expressions for the omega n and zeta. Here is the characteristic equation, lambda I minus A, determinant equals 0. So let's do that. Minus A, here is minus YV, U naught, minus NV dash, minus NR dash. And feel free to drop the dashes if you don't like them. I will not, I will not nitpick upon you of these dashes. If your life depends on it, you can figure it out later. Here, for the sake of this course, to focus on the physics, feel free to drop the dashes if you want. That's fine. Now let's add lambdas over the diagonal. Here is lambda and lambda. This is lambda squared minus YV and NR dash lambda plus YV times NR dash plus NV dash times U naught. And I'm gonna remind you guys, where is the definition of V? Here. Similarly to the last time, if beta is this thing, so any term, any stability derivative underscore beta is the same stability derivative underscore V multiplied by U naught, okay? So this thing, NV dash multiplying by U naught, this is indeed nothing but N beta, okay? And you guys are experts on this. This is a second order characteristic equation. What is the free term?
Natural frequency.
Yes, squared. And this 2 zeta omega n, right? And everything with subscript Dutch roll now. So I got an analytical expression. It's approximate, but it's fine. So let's see how accurate it is. I got an analytical expression for the natural frequency. This is N beta plus YVNR. And the zeta Dutch roll is negative NR and YV divided by 2 omega n. Why do we like to get approximations where it's not easy, it's not hard at all to get the exact values, it's just the eigenvalues of a 5 by 5 matrix? I get it less than a second in MATLAB. Why? Because these analytical expressions are illuminating. They will tell us a lot about the physics of light. Let's look at that. Omega n is the natural frequency. Always recall the mass spring system. Mass spring system, omega n is what? Square root k over m. So omega n is always associated with your spring. So here, square root of n beta. And you guys remember before, n beta is indeed my spring for the yaw dynamics. If you remember, this is, oopsies, this is what? This is, if you remember, this is your weathercock stability that is designed by what? What part of the airplane? Anybody remembers? N beta.
Vertical tail.
Vertical tail, yes. This is your weathercock stability, or a few lectures ago, we called it the yaw stiffness, right? Or weathercock stiffness. This is your spring, and it's adjusted by the vertical tail. So now by this analytical expressions, I know where to go and readjust my airplane if I don't like the performance of this mode. If these oscillations are not, if these oscillations don't die out as fast, and I need to speed up the mode, it's the vertical tail to increase your stiffness. And what about the damping ratio? Well, they should be related to the damping. This is a stiffness, this is spring, which is force due to displacement, or a moment due to angle. This is a moment, yaw moment n due to angle beta. This is your stiffness. For damping, it's what? It's force due to velocity, not displacement anymore. Or a moment due to angular velocity. Here you are, n due to r. R your angular velocity, n is your yaw moment, so the opposing. So this is, if I'm giving it a name, I'm giving this a name. Anybody remembers what is this name? If this is yaw stiffness, what would be this thing?
Yaw damping.
Exactly, this is yaw damping, right? And again, in the stability derivatives lecture 11, we derived expression for NR due to vertical tail. This is again your vertical tail, right? So you can really adjust this, the area of the vertical tail, to adjust your weathercock stability or stiffness and damping of the Dutch roll mode. This is the main benefit of these approximations, even if they are not very accurate. For the roll approximation, it was so accurate. Let's see this, how accurate it is. So the omega n here, it's 2.14 radians per second. Let's write them down. It's 2.14 radians per second, and the damping ratio is around 0.24. So this is around 9% error and 12% error. Too bad, but the main point is, even if it's worse than this, the main point is that we get to know the physics. What's my stiffness and what's my damping in this mode? What are the parts of the airplane to adjust if I don't like the behavior of this mode? Any question about that? Any question, please?
What were Professor, like, so when we're looking at like n beta, so what gives us the idea that it's related to stiffness, and then for nr, why is it related to damping?
Yeah, let's see, because we discussed this in one of the lectures. Let's see here. I need one of the lectures with the table, this golden table. This is lecture, I guess, will be maybe lecture 9 or 10. So let's get this. No, here is, no, I don't need this. Maybe lecture 9. Yes, okay, this is good. You see this, right? So we need to know what is the stiffness and what is damping first. What is the stiffness? What is, when you have a spring, what characterizes your spring? What is unique about the spring? Well, the spring gives you a restoring moment, and it's proportional to the displacement. So whenever you have a force, opposing force to the disturbance, and this force is proportional to displacement, it's a spring. And the same for the rotational version of it. Whenever you have a moment that is opposing the angle and it's proportional to the angle, then it's stiffness. So in this regard, when I have the disturbance here, what is the angle disturbance along the pitching? What is the disturbance angle? Of course, we're not talking about the Euler angles. We're talking about the aerodynamic angles, right? What is the aerodynamic angle in the pitching? Can anyone give me what is the aerodynamic angle in the pitching?
Alpha.
Alpha, right? So then the moment M due to alpha, the restoring moment M due to alpha, this is stiffness. The same here, the restoring moment N due to the corresponding angle, which is beta. This is yaw stiffness. The same for roll. L due to beta is roll stiffness. And for the damping is a force due to velocity, not displacement. So it's a moment due to angular velocity. This is clear from here. So LP is roll damping, MQ is pitch damping, NR is yaw damping, right? Any question about that?
No,
This is very, yeah. Mm-hmm.
Thank you.
Yeah, you're welcome. This is very important because, like I said, guys, in the final, the language of the final will be like this: derive an expression for the roll damping. I will not mention LP. So you need to get used of these names. And also in your interviews, if you go to Boeing and they will ask you, tell me what do you know about the pitch damping? They will not mention MQ. So NR is damping. YV is also damping because it's a force due to velocity in the same direction, right? N beta is stiffness. So we're done with the Dutch roll mode. Like I said, it's an important mode because it's annoying to passengers. It's annoying to pilots. We need to adjust this mode. We need to spend some time with it. The approximation is good, but it's not very accurate. In particular, it misses some physics. What are the physics? What are the most important physics that is missed here? So let's talk about that. Physics missed in the approximation. Actually, the effect of L beta or L beta dash, whatever you like. Well, indeed, the approximation doesn't show any effect of L beta. It doesn't show up at all. Yeah, that's right. But L beta exists in the 5x5, and it turns out that it has, here is LV, right? LV is related to L beta. So it turns out that it has effect on these eigenvalues. So it's ignored when we do this approximation. It goes into this 9% to 12%. Sometimes it's larger than this. So what's the effect of L beta? Let's see. First of all, if I'm gonna give a name to L beta, any suggestion? What is the name of L beta? What's the name of L beta?
Roll stiffness.
Very good. Roll stiffness. Very good. Roll stiffness. And if you guys remember, what are the factors? What's the geometry of the airplane that most affects L beta, the roll stiffness? How can we adjust L beta?
Dihedral.
Dihedral, very good. So I actually have several sources. We have dihedral. So this is the wing, if the wing has this kind of angle. What else? Anybody remembers?
Wing placement or sweep.
Very good. Wing placement. If the wing is high on the fuselage, then it gives you more negative L beta. L beta is negative, of course. Must be negative for stability, and all these sources give you larger negative L beta. And like you guys mentioned, the sweep angle, right? All of these give you larger negative L beta. There is one more source, which is the natural, when you have the airplane, the wing is loaded, right, by a lift distribution. It's just clamped at the root. So it acts like a cantilever beam. So it bends up like this. And this is like inevitable. It's unavoidable. It's just natural. response of the wing. And if you can see, looks like a dihedral, just a curved dihedral. So it gives you more negative L beta. So all of these factors increase your L beta much. And let's see what's the effect of increasing L beta on the Dutch roll mode that is neglected by the approximation. So again, this is the real axis, this is the imaginary axis. You guys have seen root locus, right? What's the root locus?
Yes.
The root locus is, you start with the eigenvalues at some reference value. I need to study the effect of L beta, right? So let's get a reference value for L beta. What are the eigenvalues at this reference value? Here. And then the root locus allows you to track how these eigenvalues, which are important to you, change as L beta is increased. So this will be the behavior. So this is the direction of the eigenvalues as L beta increase in negative, okay, increase in magnitude, right? So what do you think? What do you get from this sketch?
Large magnitude L beta will give you an unstable system.
Exactly, right? Because after a while, then these will cross the imaginary axis, and the system, what system? We're talking about the Dutch roll mode, which is an annoying mode. It's fast, relatively fast mode. If it becomes unstable, then this will be quite dangerous. In particular for this airplane, if actually we multiplied L beta by 20, I know this is a very large number, but if we multiplied L beta by 20, here are the eigenvalues. The eigenvalues, yes, they become the lambda Dutch roll, they become 0.43, it's positive real value, plus or minus 4.52i. So look at this, it's fast, right? Because these are large numbers. So in particular, this is the real part, right? So it's like half. So 4 divided by half is like 8 seconds, and then so this is the lambda Dutch roll if the L beta increased by 20 times. So anyway, on the back of your mind, always remember that if this L beta increased much, it worsens the Dutch roll mode. And the Dutch roll mode is something that we cannot mess up with. We can mess up with this blue mode, which we did not talk about yet, because it's slow, okay? The Dutch roll mode we cannot mess up with. So we cannot let L beta to increase much. What do you mean? I mean that this sweep thing is very desired from an aerodynamic perspective. If you go and study aerodynamics, you know that any airplane that goes into transonic, we must have a sweep to delay the drag rise. So this is something that we don't have any choice over. The aerodynamic designer will always do. And you know that this is also something that we don't have any choice over. This is actually inevitable. This is nature, right? So we don't do anything with this. So now, this is the only thing, the dihedral, the sitting angle of the dihedral that you have control over. So this is why if for some design configurations, if we have a high wing in addition to these two, then this is too much. This is too much of an L beta to the extent that we actually use anhedral in this case. We typically see this picture. If the wing is high, then we do anhedral, okay? The opposite of dihedral, to decrease the effect of L beta from all these factors, not to mess up with the Dutch roll. Any question about that?
I just have a quick question about the Dutch roll.
Yep.
Yeah, so when you wrote it out, how come we didn't include the side force due to the yaw up in the, the derivation?
That's a very good question. Thank you. Actually, it's not even included here. That's a very good question. This should have been YR minus U naught, okay? So the actual value here should be YR minus U naught, but U naught is very large and YR is typically smaller, much smaller. So we typically ignored YR with respect to U naught in most of the first order flight dynamics analysis? That's a very good question. Okay.
Okay. So we would have to state that assumption in that type of problem.
I mean, it's kind of a standard assumption, but I mean, it's a standard in this course throughout the rest of this course. Frankly speaking, it doesn't hurt. So actually, in my first 3 years teaching it here, I was considering it. So it doesn't hurt much. You just move with this YR all the way. But I found it really doesn't affect the number. So it's good to just remove it for the sake of simpler expressions. Other questions? All right, so we're done with the Dutch roll mode. Let's go to the last mode, and probably the most interesting from flight physics. It's not interesting in the sense that, like I said, it's not very important, even if it's unstable, and indeed it's unstable for some airplanes. But that's fine. Pilot will have plenty of time to overcome for its instability.
Professor,
yes.
Before you move on, one quick question. You mentioned that Dutch roll has a reason for it being named that.
Yeah, I mentioned that. Did you? I said this looks like skating. And
okay.
The Dutch people are really famous for skating. This is really I know it's funny, but this is the real reason for why it's named Dutch roll.
Okay, I missed that. Sorry. Thank you.
That's okay. So the last mode, the blue mode, is the spiral mode. And we'll know why it's named spiral mode. The airplane obviously goes into spiral. Let's see, this is not an easy mode to study, but it's quite interesting from flight physics. So let's please start fresh. Let's give yourself some fresh time now. I'm gonna take some time. It will take quite a bit of time. First of all, like I said, it's stable, but sometimes for some airplanes it's unstable. It's too slow, so it's fine to be unstable. Let's, as usual, get the eigenvector, corresponding eigenvector. Here is the corresponding eigenvector. I think I have a better one. Yes, here. Very good. So in this mode, I consider the 5 variables because it's hard to actually determine. So let's see. It's hard to determine what are the variables that are most associated with this mode. Let's see. First of all, this is side slip, this is roll, and this is yaw. These are aerodynamic variables. I'm gonna classify these are aerodynamic variables. So these are aerodynamic disturbance to my airplane, right? Phi and psi are inertial. These are the attitude, the angles of the airplane with respect to the horizon. So I'm gonna classify them as inertial. All right, so let's look at the aerodynamics and let's see among the aerodynamic variables. So these are rates, just also to remind you, these are rates, right? These are angles. All right. So it seems that the yaw angle is changing much, and also the yaw rate is changing more than the roll rate. So it seems that really, if I am to pick, because the difficulty comes from the fact that it's a single eigenvalue. So I need at the end of the day to decide about one state. So if I'm to pick, I'm gonna pick the R dynamics, because it seems that the yaw dynamics, the yaw angle is the larger among the two. The yaw rate is the larger among the two. So the R dynamics, if you recall just the R equation from above, from the original equation, it's simply NV times V, NP times P plus NR times R, right? And there is the input effect. If you're gonna consider the R dynamics, so this is R and this is R, what are you gonna do about the other two? So I cannot completely ignore them, because if I completely ignore them, this will be pure yaw dynamics governed by the yaw damping NR. Even from a problem solving perspective, what is NR? Let's look at NR. NR is negative 0.76, right? So remember, if you ignore this, you will have R dot equals negative 0.676 times R. It's like X dot equals AX. So this will be my A matrix. It will be my eigenvalue, negative 0.76. Obviously, this is too far from the real eigenvalue. Negative 0.76 is here. So this is too far. It doesn't represent your dynamics. It gives you something else. This is pure yaw. So it's not the thing. So I cannot completely ignore this. We need a smart way of doing it. And just to satisfy you, this is still under research. What is the best approximation of the spiral mode? But I'm going to tell you what is the standard thing that the community has nowadays. The community decided to do the following. Well, we cannot ignore these two. So we're going to do the following. I'm going to ignore one of them. Let's pick one of them, say P. But in the same time, use the P dynamics to get V. So when you ignore P, but still use its dynamics, it's as if you're accounting for it in an indirect way. So here is the P dynamics. It's similar to this. This is P dot is LV times V, LP times P plus LR times R. And we're going to ignore the P. But then we use this P dynamics. We use this P dynamics to solve for V and get rid of it. Let's solve for V. So this is negative LR over LV times R. And we're going to substitute it here. The resulting equation, I know that this is a bit confusing, but it is the best approximation that the community has so far for the spiral mode. It is not accurate, but it gives you very good understanding of the physics. We're going to discuss this in a minute. Let's substitute V here. So I have I have R dot equals NV times V. So let's substitute for V. It's LR times R over LV. And again, if you're bothered by the dashes, drop all of them. Plus NR times R. So I have R from here and R from there. So let's collect them together. So I have R dot is equal to NR, right? LV minus NV LR over LV. This is all times R, right? And I'm going to drop the dashes actually, just to focus on the physics. And I'm going to remind you, because I have something V here, again, multiply numerator and denominator by U naught. So everything will be in terms of beta. Because when we have some things in terms of beta, I can identify stiffness and damping. So the mode, the equation, the spiral, what happened here? Okay, spiral approximation is simply, and again, this is a standard, so you feel free to use it directly without derivation. This is NR L beta minus N beta LR over L beta. This is all multiplying R. It's one state. So this is my X dot. So X dot equals A matrix times X. But this A matrix is just a scalar. So as we know, this will be simply my eigenvalue. Lambda spiral approximately is NR L beta minus N beta LR over L beta. And I'm given all these stability derivatives, so I can go and estimate this. So if you do that, how much is the spiral? You get, let me see the lecture notes here. You get negative 0.16. So it's not too close to the negative. This is almost negative 0.01, right? But still, it gives you something here, right? Around here. Quantitatively, it's not accurate, but qualitatively gives you the qualitative physics. How is that? Let's see. Let's see. Let's first of all identify each one of this thing. We discussed L beta. Really, we just finished discussing L beta. Is the roll stiffness, and we learned all the, the most geometrical parameters affecting this thing of the airplane. Okay. What else? We also discussed N beta. We know that it's the yaw stiffness. It's due to vertical tail. NR is the yaw damping due to vertical tail. So we discussed all of them either before or actually reviewed them quickly today, except LR. I actually never talked about it in the lecture before. You will find it in the lecture notes, though, of lecture 11, a complete derivation of CLR, but I did not give it in the lecture. I just left it for you as an exercise. So let's just as a quick review, how can we derive an expression for LR? I'm not going to derive the expression, but at least I will sketch the derivation with you. Remember, I'm talking about LR now. So just a review for you how to derive these things. LR due to wing, for example. Well, so I need to apply R, a disturbance. R is the yaw rate. So it's an angular velocity about Z. So I sketch the other plane, that is XY. So this is the XY plane. Sorry about the bad drawing. And this is my wing, right? This is Y-axis. This is X-axis. And let's get the effect due to the wing. So first of all, let's apply this R. This is my positive R, right? Yaw rate. And let's see the effect on the wing. Well, the right wing will go backward. The left wing will go forward. So if I have a station here that is distance y from the center, it will go backward by how much velocity? Can you tell me?
RY.
Very good. Very good.
Not minus RY?
RY, and this will go forward by RY, right? But remember, they were moving forward by U naught, right? So the velocity here is indeed now, the total velocity here is U naught minus RY, right? Whereas here, in the other thing, it will be U naught plus RY. So the right wing is seeing or experiencing smaller speed with relative to the surrounding air, and here larger speed. Larger speed means what? What do you think? Larger speed means what?
More lift.
Exactly. Lift goes with the speed square, folks, right? So this is larger speed, so larger lift, smaller speed, smaller lift. So what will happen in terms of rolling? Because now I completely determine the effect of R on the wing, on the lift on the wing. Now, what do you want? Here is my output. It's the L, rolling moment. So how can you get the rolling moment out of that? Multiply this by the arm. So the airplane will roll to the right or to the left. Let me have the axes to see your right and your left. So this is the Y. This is Z. From this picture, the airplane will roll to the right or to the left?
Clockwise.
Yeah, this is right or left. So the airplane in this, when I sketch this, the airplane is moving into the page, right? Into the page. So this is to the right or to the left of the airplane?
Right.
To the right, yes. So this is the results. What color maybe? To the right, and this is positive, right? The yaw moment and roll moment, the sign convention with the right hand rule, positive to the right and negative to the left. Okay. So CLR, actually, we derived it in the lecture notes. You will find it as CL over 6. 1 plus 3 lambda over 1 plus lambda. CLR is positive. Lambda is the taper ratio of the wing, is positive, and this is the lift coefficient of the airplane. It's not the CL alpha. It is for the first time we don't have CL alpha. We have just CL. Why? Because this effect is not due to alpha changes, it's due to speed changes, right? So it's the total lift coefficient. Anyway, CLR is positive. Why? Because when you apply R positive, you get L positive. When you apply R to the right, if the airplane experiences a yaw rate to the right, a positive roll moment generates, which is to the right. So this is a destabilizing effect if the airplane yaws to the right, and natural roll moment will occur also in the same direction to the right, okay, causing the airplane to departure from cruise. Any question about that? This is again natural without the interference of the pilot or autopilot. So this is CLR effect is a positive, it's a destabilizing effect. We did not discuss it before in lecture. Any question about CLR? So CLR is a coupling between yaw, R, and roll, L. Natural coupling from the wing. The wing is the main contributor. Also, the horizontal tail gives you a similar effect, but the wing is larger. And it's destabilizing. Remember this. Any question about that? Fine. So we got the LR and we know the rest. Let's get back to the spiral mode. For stability, of the spiral mode, we need the eigenvalue lambda. We need the eigenvalue negative or positive?
Negative.
Yes, very good. So we needed negative, right, in the left half plane. So let's look at this. I have L beta in the denominator. Anybody remembers L beta is positive or negative?
Negative.
Negative. Very good, Derek. And just an advice for you guys, even for interviews, whenever you stick, just say negative, because the chance for things to be positive is quite small. It's only N beta for the stability derivatives. Anyway, so yes, L beta is negative. So for this thing to be negative and the denominator is negative, I need the numerator to be positive, right? So for stability, I need this to be larger than that. So NR L beta, and I will use the coefficients. It doesn't matter, right? NR L beta to be larger than the other way around. N beta LR. This is for stability, which means that, so this is for stability coming from where? This condition comes from the approximation, okay? Okay, so we're not sure if this is right or not, or wrong, right? The approximation itself is not that accurate when it comes to numbers quantitatively. We're saying that qualitatively captures the physics of the mode. Why? Let's see, because it's for stability, gives you this condition, which means that if these two are larger, the airplane will be unstable. So let's try to understand from the flight physics, why if these two are larger? In particular, why if this guy is larger than this guy, so the right-hand side is large and the inequality is not satisfied? Why if this is the case, the airplane will be unstable in spiral and go into a spiral mode, spiral divergence? Why from flight physics? Let's try to get that now. So I'm gonna review with you the requirement for stability when we have a side slip. Actually, we had two requirements for stability. So here is an airplane. So this is my Y body and this is my Z body, which means that the airplane is moving into the page. The airplane is side slipping in the positive direction, which is to the right. If the airplane is slipping to the right, can you tell me, please, what is the stability requirement for this airplane to be stable and for this side slip to die out, to be opposed? You want this airplane to roll to the right or to the left?
To the right.
If it rolls to the right, then this will be the left vector, right? And the left vector will now have a component in the direction of v, increasing v even further, right? So I need actually the opposite. I need the airplane to roll to the left. So this is, oopsies. This is the required rolling motion. So that now this is the left vector, and it has a component to the left, so acceleration to the left, i.e. opposing to the disturbance v. Any question about that? So this is why the requirement, this is actually the origin or the reason for the requirement that L beta must be negative. Okay, this was the requirement for L beta to be negative. Roll stiffness. Any question? But this was not the only requirement. There was another requirement, the other plane. So again, I have the same thing. So my airplane is skidding. So this is my total velocity vector. So indeed, this is my little v. All right, this is your x and this is your y. Now, look at this picture, please, and tell me, how do you like the airplane to yaw? To the right or to the left?
To the right.
Very good. The airplane must yaw to the right. Why? To face its velocity vector and kill the side slip. We know that it's gonna lose the heading. That's fine. The heading is an ignorable coordinate, but the side slip is not ignorable. Okay. So, okay. So we need the airplane to yaw to the right. So we need a positive yaw moment because positive is to the right. So this is actually the origin of the requirement that Cn beta must be positive. Okay. So in conclusion, when the airplane is skidding to the right, I'm assuming some direction, say to the right, I need two effects to happen simultaneously. I need the airplane to roll to the left and to yaw to the right. I never want the airplane to roll and yaw in the same direction because this will cause departure from cruise. Of course, it will go and do steering in that direction, okay? Any question about that? Any question? Fine, okay, so we reviewed these things and actually this, I mean, this was a long time ago, fine. Now let's go back to this. You're telling me that if Cn beta is large, quite larger, and Cl beta is small, then this will cause instability. Why is that? I mean, so I have Cn beta positive and I have Cl beta negative. So I have the elementary, I have this stiffness. Remember, I have a stiffness in each direction individually. But this is not sufficient for stability because they may interact with each other, resulting in instability. How is that? Let's see. If this thing is larger, if this thing is large and this thing is small, let's see what happens. Okay, so the airplane will yaw to the right as desired. Very good. So a yaw moment will be generated to the right in the right direction. But it's large, fine. Yaw moment to the right will cause what? Of course, yaw rate to the right. The airplane will have a yaw rate, right? And if the airplane has a yaw rate to the right, remember this CLR thing, we just discussed it in detail. The CLR, if the airplane yaw to the right, the yaw rate will cause a roll moment to the right in the same direction. So this is L in the same direction because of this destabilizing effect. So here, that's easy. We know that this Cl beta is negative. It will create a roll moment to the left. That's fine. And now we have two competing mechanisms. I'm sorry, this is L. We have two competing mechanisms. Some mechanism wants the airplane to roll to the left due to the roll stiffness, due to the dihedral and all these other effects. And some other mechanism due to this coupling between roll and yaw that wants the airplane to roll to the right. So let's summarize here. The airplane is skidding. there is side slip to the right, little v, and side slip angle beta, positive, to the right. At the beginning, immediately after the disturbance, the airplane will have the stabilizing behavior. It will roll to the left and yaw to the right. But this yaw to the right is quite strong. So it will cause the airplane to have a large yaw rate. And we know that because of coupling, when it has large yaw rate, it will have also large roll moment. Now we have two moments. One is large. One is large and one is small. So this one will outweigh and will overcome, and the airplane eventually will roll to the right, in addition to yawing to the right, which means that it will depart. It will go into a turn, and going into a turn, actually steep turn. When you go into a steep turn without manipulating your lift, you will lose altitude, so you'll go into a spiral down. Okay, so this is why it's called spiral. And indeed, this mode, even though it's not quantitatively accurate, it qualitatively captures the physics. Why? Because it is this approximation that gives us this inequality, indicating that when this is large and this is small, spiral will happen. And it's indeed the case, can be explained like I did from the flight physics. Questions? I know there is a lot here, but hopefully it's clear enough. And the lecture is being recorded. You can go and redo it on your pace. Any question about this?
Yeah, Professor, I have a question.
Yes, Abdullah.
So does the large yaw induce the rolling, or is it the other way around?
Yes. The large,
the yaw is what induces the
large,
moment.
Yes, exactly. The yaw induces, the yaw is, I mean, simply put, without all my complications, at the beginning, the airplane will roll in the right direction, which is, no, I don't want to say the right direction. Will roll to the left, right, here by roll stiffness, but yaw to the right. But the issue is that the yaw is strong, and the yaw is always associated with the roll moment. So the roll moment coming from the yaw is too strong and will overcome this thing, simply. Okay. So this gives you an idea about how things are really coupled together, and how even though you have stiffness, you have spring in each direction individually, it's not sufficient for a multi-degree freedom system, because things may interact with each other, causing instability for the overall system, even though each axis on its own is stable. All right, so let's get some a little bit more physical intuition about some physics here. Let's recall this inequality down here and play with it for a little bit. So what? Let me actually copy it. All right. So if we want to make this stable, although we don't have to, by the way, like we, as airplane flight mechanics people, we are not too worried about, again, like I said, this is a too slow mode. Pilots will not bother if it's unstable. That's fine. So we will not spend too much time and effort trying to stabilize this thing, and we will come back to it later. But if we want to stabilize, let's see, if we want to stabilize, which means that we want to satisfy this inequality, right, coming from the approximation. So let's recall, this thing is inevitable. It's CL over 6, 1 plus 3 lambda over 1 plus lambda. This is, I have no control over as a flight mechanics person, because it just depends on the flight condition. It depends on CL. I can't touch the CLR. Fine. What about CN beta? Can we decrease CN beta by decreasing the vertical tail? Well, of course we can. I mean, we're going to save weight and drag and very good things, but now you're messing up with what? You're messing up with what if you decrease the vertical tail?
The weathercock stability.
Very good, weathercock stability, which will affect what mode? What mode here? It will affect the Dutch roll mode. Remember here, the Dutch roll mode, this will immediately affect. If you decrease your N beta, you're decreasing the speed of the response, the omega n of the Dutch roll mode. And we said Dutch roll mode we can touch, right? We cannot mess up with it. It's not we can touch, I'm sorry. We cannot mess up with it. We cannot worsen it. If we can, we should always enhance it, but we cannot worsen it because it's quite bothering to passengers and pilots. So I cannot, at my own discretion, decrease Cn beta. Although I can if I want, right? But I will not be able to do so because I will you know, you got the idea. I will make the Dutch roll mode, which is very important mode, to be worse. Okay, so that's fine about, I cannot decrease the right-hand side. So let's go and try to increase the left-hand side to satisfy the inequality. What about CL beta? Can we increase CL beta? Well, yeah, I mean, you have several sources. You have gamma, you have sweep, you have many sources to increase CL beta. Any concerns, folks, about increasing CL beta?
Leads to instability.
I'm sorry, say it again, Fernando.
It makes the system unstable, right?
Exactly. What system? What part of the system will go unstable? What mode? It's again the Dutch roll mode. This root locus. These eigenvalues were for the Dutch roll mode. If L beta increased, it will worsen the Dutch roll mode. It may not go unstable, but it will be at least less damped. So again, I cannot worsen the Dutch roll mode. So unfortunately, I cannot play with this or that. What about the CNR? Can we increase the CNR? Any idea, folks? Any suggestion for how to increase the CNR? How to increase the CNR of an airplane? What is CNR? Ignore the C. C is for coefficient. What is NR? What is its name?
Yaw damping.
Yaw damping. Very good. How to increase the yaw damping for an airplane?
You have to change the vertical tail, right?
Vertical tail, exactly. Vertical tail. So I can increase my vertical tail to increase CNR to satisfy this inequality, but unfortunately, increasing the vertical tail will increase CNR and CN beta by the same amount. I didn't do anything. Both of them, they are proportional to VV or SV, right? So it's a predicament, right? And but the good thing, the good conclusion is that if I can increase CNR, this would be the solution, but not from increasing vertical tail. If I can do it artificially, that would be the solution. And this is indeed the solution, is to have an artificial yaw damper, which every modern airplane is equipped with a yaw damper. What's that? So you have your airplane here. We simply put a gyro to measure your yaw rate R, multiply by a gain, and go here. This is the command of the pilot. So we go and move the rudder servo by this signal. So in this setting, what is the equation for the control law for my delta rudder, my input? It's simply a gain times the yaw rate R. And if you apply rudder, what will happen? Well, there's gonna be a change in the yaw moment. It's simply Cn delta R times delta R. Let's substitute, please. So Cn delta R times K times R, right? So look at this. I have Cn equals something times R. So this thing must be what? Must be CNR, or the change in CNR. And this is artificially achieved through feedback. So indeed, your total CNR, the total yaw damping, is your original value coming from the vertical tail plus the delta CNR artificial. So you can adjust your gain to get whatever addition. Sometimes we indeed multiply the original CNR by 5 times through feedback. If we do that with changing the geometry of the airplane, we need to multiply the area of the vertical tail 5 times. Of course, this is not, nobody will allow you to do that. All right, I'm done with today. Any quick questions?
Professor, can you go over, so when we arrived at that, like the inequality that you've written right here, how did we get to that from our
Yeah, that's good. So first of all, we derived an approximation for the spiral mode. Spiral mode is one eigenvalue. So at the end of the day, do whatever you like, get me one equation. Okay, so the community choose this equation, r dot equals. Okay, so there is a procedure. This is what we explained in this lecture, right? There is a logic behind. Okay, it's not the most sound logic, but it's intuitive. Okay, so we got to this one equation which should represent this one eigenvalue. It's r dot equal something times r. So it's like x dot equal something times x. So this something is really my A matrix, and the A matrix is just a scalar now because these are just a bunch of numbers. When the A matrix is just a scalar, the eigenvalue is the same as the matrix, right? So this is your eigenvalue. So simply, this is your eigenvalue. So for stability, the eigenvalue must be negative. And because the L beta is negative, so it means that the numerator must be positive. So simply, this thing must be larger than this thing. This is the origin of the inequality, okay?
Okay, and then from there, we just...
Yeah, here, look at this, CNR, CL beta must be larger than CN beta, CLR. This is the inequality.
That makes sense. And then, but to go from just N and L to CN, CL, that's...
The C is, yeah, because because it's as if you're dividing normalizing all of them by 1/2 rho U squared SB, right? So all of them will be C's, coefficients, right?
Okay.
Yeah. Any other questions?
Professor.
Go ahead, Abdullah.
Okay. Can you explain the concept of the yaw damper one more time?
Of course.
I didn't really get it.
So, but let's first agree that, did you agree on here that if I have a means to increase CNR, my yaw damping, artificially though, not through increasing the vertical tail, this would solve the problem. Do you agree about that?
Right.
Very good. So let's do it artificially. This is actually super simple. What is CNR? Oh, of course, C is coefficient. So let's trash C for a moment. It's NR. What is NR? NR is yaw damping, is yaw moment N due to R. The airplane does it naturally through the vertical tail. Well, okay, I can do it on my own. I can also sense R and apply N proportional to R. How can you apply N? I'm going to apply N through the rudder, through my input. So, so this is exactly what we're doing. I'm sensing R. It's exactly like the airplane does it naturally, interestingly. The airplane senses R and applies a yaw moment proportional to R. And the proportionality constant is simply this NR. So I'm going to do the same. I'm going to sense R. I'm going to put a sensor gyro to sense R. And I'm going to apply yaw moment through my rudder, which is proportional to R. So I'm going to multiply it by a K. And I'm going to adjust this K to adjust the proportionality constant. Any question about that?
So far, so good.
Could I ask, are you basically just increasing the rudder angle a little bit with your gain constant?
This will be continuously happening during flight. And it depends, the rudder angle will depend on R. So, okay, let me see. There is a rudder angle for trim if needed. Usually there is no, okay. There is a rudder angle coming from the pilot command. I'm not talking about that. I'm talking about the additional rudder angle for feedback control. This is proportional to the R, the yaw rate of the airplane. So if the airplane is not doing any yaw, there's going to be no rudder deflection coming from this control law. Okay, it will only be activated whenever your sensor senses some non-trivial R. Okay.
Okay, that makes sense. Thank you.
Yeah. Questions? Sam, I think you have a question, or it's answered already.
Yeah, Professor, I was curious. This sort of, I mean, everything you've said today makes sense, but I feel like I'm doing mental gymnastics. I'm curious, do you have a recommended way for studying the logic? Like, I mean, short of just going through it over and over, is there like a series of problems that you can try and work through to help make it all make sense? I don't know. Is there something you recommend?
Yeah, so this lecture and the last lecture is not actually about problems, rather about the physics. So I'm not, frankly speaking, if I'm gonna test you about this, it would be multiple choice, like maybe what happens to the Dutch roll mode if I increase roll stiffness, kind of thing.
Yeah.
And then give you some options. So it's not about problems. The problems will be super simple, like you have these two equations, for example, for omega n and zeta for the Dutch roll mode, right, at your disposal in the cheat sheet, in the lecture notes.
Yeah.
And you have these as given numbers, and I'm going to ask you, find the natural frequency and the big ratio of the Dutch roll mode. So this is super simple because it's just substitution in the equation. So as far as problems are concerned, they are simple, but there are lots of physics going on in this lecture. You can study the lecture. The lecture notes are very detailed. I highly recommend that you guys read them.
Okay.
In this lecture is recorded, you can go back and play it again and think about it. You can also read the book section on that part. But these two lectures are very important. In the flight physics, again, it's not for the final, it's for the flight physics. This is where everything comes to culmination.
Yeah. Okay. Yeah, I'll go through it and, use my little toy airplane to try and think it through.
Yeah. Yeah, if I'm in the lecture in person, I would have my little airplane here with me to explain things, but unfortunately we're deprived of this.
Yeah. Thank you.